Hello and welcome to today's webcast brought to you by Laser Focus World. I apologize for the late start. We had a small to medium technical difficulty. I'm happy to note that today's event, Infrared Sensors and Systems, an overview and tutorial, will be presented by Martin Richardson, Professor of Optics and Photonics at Creole, the College of Optics and Photonics at the University of Central Florida. Today's webcast is sponsored by Teledyne DALSA and Sierra Olympic Technologies. This presentation is both live and interactive, so you can ask questions at any time by clicking the Ask a Question box in the presentation window and clicking the Submit button. And we do encourage questions. We'll hold a short Q&A session right after Martin's presentation. For those in the audience who want a copy of today's slides, a PDF of today's presentation is available in event or will be available by the end of the presentation in the Event Resources section below the Q&A box. If you are running pop-up blocking software, you'll need to disable it to view this webcast. In addition, it's recommended that you close down all other applications for better performance. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It will also be accessible from our homepage at www.laserfocusworld.com. Now it gives me great pleasure to introduce our presenter, Martin Richardson.
Hello, everyone. It's a pleasure to be on this webcast. It's rather a new approach for me to disseminate science in terms of mass audiences. And of course, I don't have a very good understanding of who else is listening in, but I hope I will be able to interest and entertain you for the next hour or so. I'll try and keep it to the hour time scale despite the slight delay in starting. First off, this will be somewhat tutorial in nature, but I want to be able to cover enough ground to hopefully capture the interest of most of you that are listening. First of all, I'd like to acknowledge some local colleagues who have helped me put this presentation together, particularly some professors here at the University of Central Florida, Ron Driggers, Kathleen Richardson, who's my spouse, and an expert in optical materials, and Ken Shepler, who is now here at Creole. He, of course, was a research fellow at AFRL in some years back. So I've divided this presentation up into several sections, and hopefully we'll be able to get through all of them. First off, I'll hopefully we can get on the same wavelength with regard to definitions of the mid-IR and some of the broad aspects of why it's such an exciting area of technology now. And then we'll cover in sequence, not totally comprehensively, but highlight the advances, particularly recent advances being made in sources of the mid-IR, in new materials for the mid-IR, a very exciting area, particularly as far as they affect the optical components, and then we'll summarize to some extent the advances being made in the mid-IR detectors, certainly their current capabilities, and how they're used in mid-IR technologies for sensing in particular. And then if there's time, I'll summarize not a comprehensive approach to photonic applications in the mid-IR, but really just to mention two, namely materials processing and defense and security applications, not in any total manner at all. So let's just get through with some of the introductions. Firstly, the definition of the mid-IR. I mean, many people are familiar with the visible and near IR region being in the region of the electromagnetic spectrum being up to the region of around 1 to 2 microns. In earlier times, it was specified up to 3 microns, and in fact, the mid-IR region was defined as going out from 3 microns to 30 microns. But in today's vernacular, I think we're more talking about the near IR being up to 1 micron. We talk about the short wavelength IR being from 1 micron to around the 2.5 micron, and the middle wave IR being out to 5 microns, and long wavelength being out to 14, 15 microns or so. And these definitions really are defined by interest areas. Obviously, the transmission of the atmosphere, we'll go into that in more detail, but you'll see on that middle section there, middle graph there, where these separate annotations define the transmission windows of the atmosphere. But more important aspect perhaps is that these definitions are really defined very clearly by the types of materials that we are able to use in these different bands of what I will call mid-IR. So mid-IR will, in essence, cover both the SWIR, the mid-wave IR, and long wavelength IR. Just a quick comment in passing. Clearly, there are very great differences in analyzing and recording radiation from different regions of the spectrum. So what's shown here is relatively recent photographs of our galactic center. On the left-hand side, it's in the visible, and on the right-hand side, the same image, but now taken in the infrared area. And of course, you can see significant differences in the two images, certainly taken from the cosmos. Very quickly, let's go through just the definitions of energy, wavelength, and frequency. I'm not sure how many physicists or electrical engineers there are listening to this presentation, but for those of you that aren't, we're talking about wavelength in terms of meters or nanometers or micrometers. We sometimes use the expression the wave number, which is in our definition here defined as 1 over the wavelength in centimeters. And there's interest, particularly for those of us that work in a number of different areas of the electromagnetic spectrum. We sometimes talk about photon energies, and photon energies are obviously invoke the use of Planck's constant. And I put down here some canonical numbers of relating wavelength to photon energies. And of course, the photon energy is in terms of electron volts, and there's an expression there for the value of the electron volt in terms of energy, which in joules in this case. So to give some reflection on how important the mid-IR spectrum and mid-IR photonic technologies are taking off, we can make some comparisons, at least on the market. Up in the top left-hand side is one indication of the total laser market as of around 2016. You can see that the total laser sales are around the $10 to $12 billion market. And with a growth rate, average growth rate around the 10% mark. The mid-IR market is smaller. If you look at the bottom graph, bottom left graph, you can see that in 2015. The mid-IR market was, depending upon how you measure it, at the level of $1 billion or so. But you can see from the growth rate, just from that curve itself, it's rapidly grown now to several times that. In fact, the two other graphs shown here would show in infrared detectors, for instance, cage growth rates of up to 17% or so. So this illustrates that mid-IR and technologies in the mid-IR are in a state of rapid expansion, and that, of course, is being driven by many of the new technologies that we're going to be talking about this afternoon. So let's begin with mid-IR sources. What's shown here is a compendium of coherent sources, where we'll be largely dealing with coherent mid-IR sources. And there is, at the present time, a lot of research activity on a number of different types of mid-IR sources, starting with, in terms of solid state materials, the rare earth solid state lasers, solid state vibronic lasers, refer to those later. Semiconductor lasers have a big impact now with the development of QCLs. There are a large number of parametric processes that we can use, nonlinear optical processes that we can use together with laser sources in the visible and near IR that in essence create coherent sources in the mid-IR. These include OPAs and OPOs, harmonic generation and difference frequency generation, and the like. There is an increasing effort now in nonlinear mid-IR fibers and potentially fiber lasers that are based on new materials in the mid-IR, and some activity also going on in microresonators. These progress is illustrated in the two other figures that I've shown here. You see how it can be broken up into solid state, fiber, semiconductor, and nonlinear sources, as I mentioned. And of course, there are a number of different approaches. If you look at the right-hand figure, there's a number of different approaches in terms of starting from mid-IR or creating mid-IR hybrid lasers using different primary laser sources such as holmium-YAG or thulium-YAG, or other types of sources, or chromium-based sources. The next figure, in fact, shows a somewhat different presentation of this, but highlights the principal laser sources. We shouldn't forget that in the mid-IR we have had access to high-power CO2 lasers and indeed CO lasers for decades now, and there is still development going on with these laser systems, particularly towards high average powers and high repetition rate pulsed laser systems. Pulsed laser CO2 laser systems, in fact, now are the laser source of choice for EUV light generation for chip manufacture. And in fact, this is a multi-$100 million market at the present time. But where we'll concentrate today is really on new sources of new solid-state sources, particularly compact sources that can be made cost-effective, ruggedized, and the like for applications in industry and in various industries, I should say. So there are direct solid-state lasers, and of course, as you notice on the bottom of that chart, there are a number of different approaches towards frequency conversion based on different sources, even sources in the near IR, particularly say neodymium and ytterbium sources were operating around 1 micron, that through DFG, OPOs, and OPAs can provide us with coherent light sources stretching through beyond 10 microns out to 20 or even 30 microns. So you get a picture of a very dense field of development along many different pathways, and we won't be able to cover all of these pathways in any depth in this presentation. So consider this more to be a review of the overall, and perhaps with some indication of where the most rapid progress is occurring at this point in time. I've listed here a few texts, most of them recent texts, on mid-IR sources. That includes more recent texts on supercontinuum light sources, and you of course can find many references in those texts. We shouldn't forget, of course, that the incoherent sources also play a part in mid-infrared technologies. Shown here or listed here are the advantages and disadvantages of incoherent versus coherent sources. Of great laser diodes are now operating in the mid-IR region pretty effectively. They have a broad range, and of course they're inexpensive and ruggedized and usually compact. So that where useful, of course, they can be incorporated into many different systems, particularly systems that are on, say, platforms, integrated photonic platforms that are small, compact, and in nature. So the mid-IR is finding application space now their sources are finding application space now in many different areas. Obviously in spectroscopy, gas phase spectroscopy in particular. We'll go into reasons for that in a moment. In standoff detection and in IR countermeasures, and particularly in imaging. In the medical side, in nanoscale imaging, and also in material science, and as well as in microscopy. And of course, there's great potential for these sources now in the broad area of environmental monitoring. Environmental monitoring that includes basically monitoring those parts of our life which leads to a higher quality of life. So that can include food monitoring and medical monitoring in the different types of sensing systems. And you see the requirements, at least in a general sense, the requirements of these various areas in terms of the source characteristics themselves. So let's start with review several of these sources anyway. The high-powered mid-IR sources really are reliant now on fiber-based systems, more so than compared with solid-state-based systems, particularly erbium oscillating at 1.5 microns, while erbium fiber lasers can be used as a source to pump longer wavelength sources, as we'll see. The highest powers so far in the 2 micron region have been generated with thulium fibers, powers approaching, even demonstrating kilowatt powers. And adjacent to thulium in terms of wavelength, holmium fibers also showing lots of promise. Both these two lasers are important because this is a region of high transmission, as you can see. This is a region of high transmission in the atmosphere, and although those curves look nice and smooth on the figure here, if were we to expand them, then you would find that there are in fact many fine absorption lines in that spectrum in the atmosphere, and the capability to tune thulium and holmium fibers across those bands will be very important for many types of sensing and other applications where high power fiber lasers of radiation needs to be transmitted through the atmosphere. My group here at UCF is working in the development of these lasers, and I won't dwell on it very long, but just to give you a sort of sense of of the development of these lasers. They're now basically all fiber systems. This is an illustration of an all fiber MOPA system, oscillator amplifier system, using various types of optical fibers. There's keen development in optical fibers for optical fiber lasers, but also for optical transmission. And we too here at UCF have now a very strong effort in optical fiber design, fabrication, development, and testing. This is perhaps it can be illustrated on the next slide here, which shows some of these thulium fibers, what we call large mode area fibers. They can be solid in form, as shown in the photograph on the extreme left, or they can involve so-called photonic crystal fiber architecture, shown in the other two photographs. In the middle case, polarization maintaining fibers, where the average refractive index of the cladding relative to the core can be changed by, in essence, the inclusion of a large number of vacancies or holes in the fiber itself. You can see the structures of these fibers. They go to fairly large core sizes, and for high power lasers, where whether optical damage or the power loading capabilities are a factor, as well as still maintaining single mode propagation, the actual sizes of the fibers become extremely important. And of course, for pumping these with high power diodes, we need to have the highest possible numerical aperture for being able to effectively pump these types of fibers. In fact, although we associate most fibers with being flexible for optical fibers, particularly from communications, of course, there is now a class of fiber lasers which uses, in essence, solid photonic crystal fibers, literally rods of photonic crystal fibers that have fairly large dimensions, as you can see on the right-hand side. There are some references I've given you at the bottom there for where you can follow up, but of course there are many references to the development occurring with high power fiber lasers, but they are of course still limited down to the extreme short wavelength end of the mid-IR region. The spectral characteristics of these fiber lasers can be controlled. Thulium has a broad bandwidth, as I've noticed before, and can be tuned all the way across that bandwidth. But likewise, narrow line widths can be, or the lasers can be seeded with narrow line width sources, both for thulium and for holmium. And the power is driven up to the point where nonlinear modulation and instabilities start to broaden the spectrum. That, in principle, could be useful in some applications of the mid-IR, but in general is to be avoided. Fiber lasers are not the only source of high powers, particularly with ultra-short pulses. There are a number of research groups now that are working on high-intensity ultra-fast systems. Much of the effort that started off with Ti sapphire lasers in the last century and still continuing now. But now using optical parametric CPA approaches, now in some cases new crystals, we're able to generate by OPCPA ultra short pulses wavelengths beyond 4 microns. In fact, up to 6 microns has now been demonstrated at relatively high powers. I've chosen this figure here from just as an illustration. This is of the system in in Russia that was recently published, which produces 20 millijoules per pulse in 100 femtosecond pulses at 4 microns or 3.9 microns, and at repetition rates of 10 hertz or so. So these systems are now being used for many different types of investigations, scientific investigations particularly. Filamentation is one of those areas. High harmonic generation is another. X-ray generation, particle acceleration. You might say programs that are largely driven by pure science, but as we all know, pure science results in the pure science arena, in many cases, rapidly transfer to practical applications in the industry and government. Let's briefly look at other sources. Supercontinuum sources are right from the outset of ultrafast pulse light propagation, particularly with high intensities. It was recognized that supercontinuum can be produced by a number of processes, and is now supercontinuum source development is now a separate discipline on itself here, and I've illustrated that here by some of the more recent work on supercontinuum generation. On the left-hand side, you see the spectrum that is demonstrated by basically an integrated photonics supercontinuum source using, in this case here, silicon wires on silicon on sapphire nanowires, producing broadband supercontinuum light all the way from 2 microns to out to 6 microns. Of course, this is driven by in this particular case, is driven by an OPO, but the source itself is a very compact source inside a simple resonator. Supercontinuum sources were first, of course, observed in propagation of ultrafast pulses, and particularly the propagation through optical fibers. Initially through glass optical fibers, but now in particular through hollow core fibers and fibers with optical structures that are designed to specifically maximize the supercontinuum generation. As I mentioned before, the supercontinuum generation can come from a number of different processes: self-phase modulation, four-wave mixing, soliton generation, other effects. And what's shown here is a couple of notable results, recent results. In one case of optical fibers produced with non-oxide glasses with chalcodonide fibers, arsenic selenide and arsenic sulfide. And in the other case, shown with even newer fibers in indium phosphide fibers, which show some impressive results of flat continuum generation in the 4 to 5 micron region. Of course, flat spectral continuum sources are, of course, particularly of interest for applications in a number of areas. On the bottom, I just illustrate that this is a vibrant area in the marketplace. There are a number of different sources, companies now marketing supercontinuum sources based on ultrafast light pulse generation, from the larger companies like Tor Labs and NKT to smaller companies on the right-hand side. And I'm sure I haven't. There are many other companies getting into this business of creating small, compact, relatively inexpensive continuum light sources. Another way of producing infrared light sources, laser light sources, is to use transition metal lasers. This is being pursued in a number of laboratories, but I want to just refer briefly to Mirov's group at the University of Alabama. The most successful data so far seems to be with chromium or iron-doped zinc selenide or zinc sulfide host materials, and in most cases pumped by erbium lasers at 1.5 microns. Up until very recently, only modest powers, I would say modest powers, a few watts, have been generated by this approach. But more recently, using different sort of pump architectures, so-called rotating disk architecture, with high power pumps, the same group has been able to generate output powers in the mid-IR of up to 140 watts. So impressive new results in terms of laser pump transition metal lasers. If we now look at other sources of quantum cascade lasers, I won't have time to go into the principle of these, but they're basically an outgrowth of the simple diode, but much more complex in structure, both for quantum cascade lasers and also from interband cascade lasers. There's a lot of work being done in the development of these lasers, and now several companies are marketing laser radiation sources in this region. In spectrum, they now provide coherent light sources all the way from around the 4 micron region beyond 10 microns, but particularly in the 4 to 6 micron, 7 micron region. Their advantage, of course, is that they are extremely compact. They're still relatively expensive in terms of purchasing. I included here some more recent results from Daylight Solutions, one of the early time companies in QCLs, who are now producing, selling rather, I should say, a quantum cascade cavity laser. And you see below that, depending upon the material and the laser configuration, they can access powers all the way across pretty much all the way across the mid-IR spectrum. On the right bottom hand side shows the sort of or what's involved in a quantum cascade laser, at least courtesy of some photographs from Pranalytica, and of course Pranalytica, the CEO of Pranalytica is Kumar Patel, who is perhaps the doyen of the mid-infrared spectral region. He, of course, was the original developer of the CO2 laser, and now his company here is well standing, has high standing in the QCL market, and these photographs show how compact these types of lasers can be built. The laser itself, together with all the power supplies and control systems here, are all built onto basically single platforms, and that's their great advantage. So we're seeing that QCLs are beginning to penetrate several markets: the defense market and industrial markets. About half of it, more than half of it, is now still in the defense market. And you can see from the numbers here, I'm going to move a little faster here. You see from the numbers here that there is that the growth rate is substantial, not yet at double digits, but substantial in terms of overall market. So in summary, on high power sources, let you read these, and I'll just make some general sources. There's a plethora of approaches now being adopted now to create mid-IR sources, and doubtless many of these new sources will expand or rapidly rise up through the TRL levels to higher levels of industrial use, and the future looks extremely bright, not just for the new sources themselves, but of course for the new technologies that they'll help create. Let me very quickly go over mid-IR optical materials and components. I mentioned earlier that the mid-IR, in many respects, is basically defined by the properties of the materials that are used in the mid-IR. And the breadth of materials in the mid-IR region is not as great as it is in the visible region, and and the near IR region. And the primary reason for that is that we are not really able to use oxide materials in any great extent in the mid-IR. So we're limited now to traditional infrared crystals, or polycrystalline materials. We can rely on infrared glasses materials, non-oxide glasses like arsenic selenide and other materials that I've quoted here. Their great advantages is that they have an extremely wide window of transmission in the near IR, stretching out into the long wavelength IR, so beyond 10 microns. The disadvantages are that as being non-oxides, they are less stable thermomechanically. They usually have lower optical damage thresholds, and their fabrication in pristine form is also more challenging. Other materials that propagate in the near IR, well as silicon and sapphire, still have uses. The halides are interesting materials. They have transmissions out through beyond 10 microns. I well remember my days in developing high-power CO2 lasers. We would use fluorides for many optical windows and materials, but of course they suffer from being hygroscopic, difficulties in coating these materials, and so have obvious limitations in long-term, in particularly industrial use. So this slide here really shows the spectral regions that are defined by these materials. This is so much of an interesting region because of the fact that it covers what we call the molecular fingerprint region, particularly of a number of different gases, or molecules that can be in part of gases that are many of which that can be toxic. So this is the mid-IR region is one of the reasons for so much development in the mid-IR region is the capability to potentially detect very low populations of toxic materials in the atmosphere. And so we can survey the properties of these materials very quickly, either as mid-IR glasses and ceramics, active mid-IR optical devices, and very briefly doped mid-IR materials. I probably will not have time to discuss the doped materials, but there are some work now going on doped chalcogenide materials as active laser materials. So although we don't have access to oxides, we do have access to some other features of infrared materials, particularly infrared glasses, which helps us to design optimum optical components, particularly passive optical components. So you see in this region here, if we look at the curve of refractive index against the Aber number, for instance, that's in both these fig diagrams here. One, plotted against the Aber number in terms of diagrams. So basically looking at refractive index as a function of dispersion. Then there are various regions that the semiconductors work well in this region, but with high refractive indexes. There are disadvantages there. The fluorides and tellurides really only operate with very high dispersive regions, and the 2,6 crystals also have high dispersion. The chalcogenides occupy a sort of unique space here, illustrated on both these figures here. In fact, if you look at this encircled region here, this is the region of chalcogenides where there are a number of different chalcogenides, and we can hopefully be able to use these mixtures of chalcogenides to be able to design optical glass materials for specific applications. I've just briefly summarize that chalcogenides really are this group here from oxygen to telluride, but actually there's only really 3 chalcogenide materials that are really used in optical materials: sulfur, selenium, and tellurium. They're amorphous compounds of chalcogenides, or rather, glasses are made of amorphous compounds of these elements. Here's some examples of these, including phase change materials, and of course they're oxygen-free for good infrared transmission. They can be made now in fairly large volumes. Here's some large materials here that have been shown here, developed in Kathleen Richardson's group, and with increasingly improved purity, and particularly in terms of optical performance. One of the advantages of using chalcogenides is that we can engineer their chemistry to optimize their optical function. So plotted here in sort of 3-dimensional scale, here is the index versus the wavelength, the region, and their temperature. So optical designers, when they're designing optical components in the mid-IR, really need to have the capability to, or in fact do have the capability with these chalcogenide materials to, in essence, create new materials specific to optical components in specific systems. So they have the capability, for instance, to engineer the thermo-optic components which dictate how systems can be designed, even to the point of being, quote, athermal. At the same time, to be able to control or design the thermomechanical properties material by, in essence, tuning the constituents of the glass matrix itself. So there's compatibility with well-established crystalline designs, and candidates are of course essential. I'll hopefully just be able to try to mention some new work in this area, which shows that studies of these materials show that, for instance, for a glass system that contains germanium, arsenic, and selenium, by keeping the germanium, by varying the germanium content of the glass and measuring some of the physical characteristics such as the TG, the CT, and the hardness, one observes direct correlation or anti-correlation of these variation of these values with the percentage germanium content here. And this reflects itself also in the properties of the material itself, the dNdt, which is very important property in terms of the material, in terms of knowing the refractive index as a function of temperature and how it varies as a function of temperature. And you see it here, a distinct two-sided region here, where on the left-hand side on these 2 left figures here, we were basically in the region where there is a very strong correlation. This is a homogeneous type region here, where there's basically an excess of selenium, and whereas on the right-hand side, the composition is selenium deficient, and we see more constant properties of the materials as a function of the selenium material. I'm sure that my spouse could have described that much better than I can, but suffice it to say, I hope it portrays the notion that if you link chemistry and structure, then you can control properties of these glasses. In fact, Ray Hilton from Amorphous Materials, a long time back, created this relationship between the DNDT and these physical characteristics, the CTE in particular, and has quite some time back showed a nice linear relationship between DNDT and CTE, to which now more recent data has been added, which shows how the CTE can be controlled. If we can control the CTE, then all other optical components, particularly optical parameters, particularly the dispersion, can also be controlled. A new development in these designer optical materials in the infrared is in the use of, or the incorporation, I should say, of nanocrystalline components in composite material. If one can incorporate nanocrystals in a structured way into these glasses, then one can control the position where they are on the on this conventional diagram of composition, and particularly this has been demonstrated so far with this material called GAP-C, which basically a chalcogylate material with selenium, which allows us to develop compositionally agile, high transmission chalcogylate materials with extraordinarily large changes in the refractive index, and that allows for us for the experts in this field to start to think about using these materials as green lenses, for instance, and green lenses potentially will have applications in many mid-infrared systems. There's a couple of examples here of these green lenses here, and green materials. You can also see that these materials have very high transmission across broad regions of the mid-IR, stretching from 2 microns out to 16 microns. And comparison of these GAP-C materials with the base glass of GAP-C without the nanoparticles in. And you can see how on the left-hand side you can get control of the refractive index, very precise control of the refractive index across these wavelength regions by using these glass ceramics. So, perhaps in summary, here are many of the physical characteristics of these nanocomposite glass ceramics compared with conventional arsenic selenide, the GAP-C normal material, and now with these glass ceramic materials, you can see how we can get increased refractive index. Most other parameters will remain constant, but the dispersion can be decreased, and the micro hardness can be increased. So an advantage for chalcogylate materials. Of course, glasses are not the only regions. Here's a summary, a recent summary of the properties of mid-infrared crystals. Basically, 3 groups of crystals here. I won't have time to go through all these parameters, but what should be noted here is that Isaenko and his group now are quoting optical damage thresholds. So these crystals, which conventionally are used as nonlinear optical crystals or as optical components, have some advantages over glass. Of course, the disadvantage at the present time is that balls of these materials are relatively small. The optical properties of the uniformity of the optical properties and materials are still need to be improved. We're still dealing with, in most cases, many relatively small samples, small sample sizes of these materials, at least many of these materials. So in summary, we can say that the mid-IR region is in many respects defined by the properties of these non-optical materials. In tongue-in-tooth, we are unlikely to see kilowatt high-power CW beams in the mid-IR anytime soon, at least compared to visible laser systems where ytterbium and ytterbium fiber lasers, for instance, are now single high powers, single mode high power, single fiber power levels are up at beyond 10 kilowatts. But that's not the only area of development that's needed in the mid-IR. The real optimism here is that there's a rapid development of new optical materials, designer-made mid-IR materials, almost like designer-made jeans, right? And these are beginning to have a broad impact on bulk and integrated photonic devices. And many of these devices, of course, include mid-IR laser sources. So thin film integrated photonics on silicon and even on flexible polymer substrates will be able to take advantage of these new materials. And new crystals and polycrystalline ceramics will expand the capabilities of nonlinear optics in the mid-IR, both harmonic generation, DFG, parametric processes. There is particular interest now in building mid-IR polycrystalline ceramics. And although I haven't summarized it here, there's quite some advances being made now in poled materials, poled mid-IR materials, as nonlinear optical elements that could significantly impact the mid-IR integrated photonics field. Let's deal with mid-IR sensors. Unfortunately, I'll breeze through this area a little bit faster so that I can hopefully try and stay on time here. The market in sensors is growing rapidly. Mid-IR sensors is growing rapidly, and the number of different for sensing and many different materials. And these materials are shown here, the non-equivalent concentrations that can be sensed in the mid-IR. So going down to in the vertical direction, going down to certainly single parts per billion, and perhaps even getting in some cases into the 100 parts per trillion concentration. So sensing, particularly gases at these levels, is going to have a big impact on society and on industries that are going to need to have much tighter control of industrial processes that involve these gases. As a consequence, there's a big effort now being staged to create integrated small infrared sensors, some of them including QCLs, and there's some examples here shown on the right-hand side. The market is potentially extremely large. The near-term market is really that market in essence as a replacement for existing chromatography market and the FTIR market. This is a $1 billion market, $2 billion market at the moment. but new mid-IR sensors for absorption spectroscopy, emission monitoring, and trace detection, biological sensing, food sensing, for instance, are going to open up new avenues in the marketplace. So the replacement of chromatography will probably be a relatively slow process, but the excitement really is in the application of these new mid-IR photonic sensors in new markets. And I mentioned for industrial process control, drugs, explosives detection, medical applications. A big one, I think, is in the food industry and in domestic sensors that are control environment in the house and in public, bacteria control, for instance. The challenge at these stages is to acquire these or develop these technologies that rise rapidly through the TRL chain, if you like, to market and to market intervention. You know, there are the problems are in meeting the low sustainability of the supply chain, or rather depending on the low sustainability of the supply chain. In other words, these sensors are dependent on, say, for instance, light sources and even sensing technologies like MEMS optics, which themselves are changing very fast. And so the supply chain is still fragmented. Unquestionably, we'll be moving towards a more module-based integrated architectures, but that will take some time. Cost models are not well established, so in some respects this restrains market development because it, in essence, holds back the confidence and investment that's needed to drive these devices up in TRL level to the point where they're successful in the marketplace. Clearly, large reductions in swap C are needed, and the faster, or rather, the quicker the market volume can be determined, the quicker the development. So investment, of course, goes with predicted market volume. With integrated devices, you can perhaps correlate the development of integrated devices with the development of MEMS devices. MEMS, of course, is a well-established fabrication technique, but you can see in these charts here how the predicted market for those MEMS technologies that have photonics applications, like, for instance, microfluidics, which is basically in sensing, microbolometers, digital compasses. The blue areas, for instance, which show a rapid increase in volume, or rather in market size, are those areas that are now being driven by, on the MEMS side, they're being driven in part by the demand of new photonic systems. We'll quickly go over a few new and exciting IR approaches. Hollow core fibers are being used now exploited for sensing in many different areas. Just to illustrate a few major programs here on combustion diagnostics at Stanford. There's the NSF MERTA program at Princeton, which is, I think, just completed. But they're a part of that program addressed glucose monitoring in the mid-IR using optical fibers, hollow core fibers. At PNNL, there is a program there using hollow core fibers for isotope analysis, using QCL illumination and basically spectroscopic analysis of the emission from isotopes. And we mentioned several times the importance of trace gas analysis. One well-known group is the one in Bali, but there are many other groups working in trace gas analysis. To summarize on mid-infrared imaging detectors, the standard, of course, is indium bismide, and the current workhorse for mid-IR cameras. But these devices are costly and need to be cooled to liquid nitrogen temperatures and are expensive. But of course, they're incorporated in many detection systems, particularly in the military. We can look forward to MCTs, or MCTs are already being used as an alternative. They're working much closer to room temperature operation, and they're extremely sensitive. But again, the cost factor comes into their use, particularly in say for industrial monitoring systems. Quantum structures for detectors also have a bright future. The advantage there is that we use commercial foundry infrastructure fabrication techniques to build them. Detectors are improving in performance, both in uniformity and cost. As the quantum efficiency improves, this will obviously lead forward to future more applications in high performance. Here, as shown here, are a few of those IR sources that IR detectors that are currently being used based on quantum structures. IR cameras from Lockheed and QMagic Q. There are strong research groups in the universities working in this area, particularly the Rezegi group at Northwestern. And there's certainly a very bright future for quantum detectors in the mid-IR as array detectors for high-resolution imaging. Lead selenide is also another relatively new material for infrared detection, the infrared array detection. Already fairly large arrays have already been made with 60 micron resolution and fast integration times. It operates at room temperature. They're inexpensive. They have high speed, and they're almost ideal for IR countermeasures and high-FI seekers. In development of these detection systems has been driven in part by by DARPA programs, particularly the WIRED program, to help transition these technologies to higher TRL levels and into the marketplace. So these are certainly areas where we can expect to see a rapid impact of the IR detectors. So there's large potential for marketing low-cost swap detectors, and as you can see, I think these detectors are beginning to penetrate markets. They'll clearly have very large impact on industrial, food, and environmental markets, medical markets too, which will challenge existing approaches, particularly chromatography. As I say here, the R&D field is awash with these new ideas and developments, and it's going to be the market itself that starts to identify viable product pathways that squeeze the R&D investment into design, development, and test capabilities that push up into the higher TRL levels, to the levels where market fabrication and market volume can be carefully predicted, and where that feedback of market and investment in for identifiable markets feeds back to R&D. At present, the investment in some of these technologies, particularly the imaging technologies, is really driven by the defense and security market. As we go forward, then we would expect to see the other industrialized markets uses for IR sensors, particularly in the industrial and environmental and food and medical markets, start to really drive R&D development of specific sensor pathways. We're almost going out of time here, so I'll just briefly summarize the mid-IR technologies for sensing, since I assume that there are a large number of folks interested in mid-IR for sensing technologies. Of course, one of the most well-known mid-IR technologies is environmental mid-IR imaging sensing technologies from satellites. That's well established, and of course we will be seeing more satellites. In fact, there was just one more IR satellite launched, I think, this past week or so, for high-resolution mid-IR imaging of environmental factors on the Earth's surface. But of course, these are not localized detectors, and of course they are extremely expensive imaging systems. I've mentioned I've mentioned why it's so important to develop mid-IR technologies for sensing, particularly gas sensing, because of the proliferation of spectral signatures in this area. It's often called the spectral footprint region for molecules in the mid-IR region, and for sure exploitation of sensing technologies that use tunable, for instance, narrow line width sources and sensitive detection systems. There's strong expectations for new applications in having those capabilities. Let me briefly mention a couple of technologies that show great promise in terms of sensitivity. In the laser field, folks have in the last decade or so learned how to create spectral combs of in the output spectrum of CW and pulsed laser systems, even ultra-fast laser systems. And these spectral combs are indeed very useful for being able to measure, say, just in transmission, measure accurately the absorption spectrum of dilute, say, hazardous materials in the atmosphere. It could be in the industrial environment, or in the outdoors environment, or chem bio environment, or in fact even in the defense areas too, for say IED detection. This technology has been driven by a number of agencies, but I briefly mentioned here the DARPA Scout program, which has now been running for several years. And our growth of this and other programs supported by other defense agencies has been the development of dual comb spectroscopy for long-range sensing. Briefly, here we use two frequency combs of just a marginally different frequency, and but we phase lock these frequencies together, where there's a small difference in the repetition rates of these two frequencies. So as a consequence, the difference frequency of these two frequencies here provides us to have a direct correspondence between the optical and the RF difference frequency, and that can be used very sensitively towards measuring very low, spectroscopically very low levels of concentration of absorbing materials, or absorbing gases in particular. clearly there's a great need, as we've been intimating, there's a great need to be able to have integrating sensing devices on integrated platforms. And what's illustrated here is some work that Kathleen Richardson and the group at in a collaboration with Clemson University and MIT have been working on these types of integrated functional devices where it integrates different materials on a single platform. So there's one material, for instance, the functionalizational level. There's different materials, of course, for the light source, the creation of waveguides, for instance, that funnel the source light to different functional performance, and of course the detectors themselves, all on a single substrate with different materials. So the challenge here is to build these integrated platforms with multi-materials, glasses for waveguides and resonators, semiconductor detectors, of course, polymers for the perhaps analyte detection, for instance, and in some cases, for instance, to be able to incorporate phase change materials that are themselves part of the detection system. Of course, there is a plethora of different types of designs of these types of integrated photonic systems. And for them to develop past the R&D stage, past the TRL stage, TRL 1-2 type stage, it's necessary in a parallel path for the obvious market potential and the investment from the market in subsequent development of these devices to occur. And of course, they won't occur across all pathways. Perhaps I can illustrate this by almost a local example, but one that has received a lot of publicity in the last few years, and that's the development of high-speed LiDAR systems for autonomous vehicles. And I just take the liberty of just using some illustrations here from a local company, Luminar, the CTO of which, Jason Eichenholz, is a former student of mine. But the challenge with these types of devices are extremely challenging. Long-range detection, very quick response, low reflectivity, and just a few percent reflectivity, and of course, absolute reliability on functionality and detection. It's one of the hottest new industries in the photonics development. And already, $1 billion or more so has been invested. And it's been invested. Why? Because there's a clear multi-billion-dollar potential market out there. And as a consequence, it's very highly competitive. Luminar is competing with several other other companies. The challenge is extremely high. The challenge is to be able to roll these things out with very low unit cost systems that are compatible with other sensing systems and sensing devices, particularly for the automobile industry. So the challenges are high. So these challenges can only really be met in the R&D stage by having a focus on where the individual markets are going to be. This is not a mid-infrared detection system, but my point here is that it takes the market to focus. It will take the market to focus attention on the pathways that need to be developed in the mid-IR. So I've tried to summarize that here. I won't go through all these points here, but I've made some of them already. We are rapidly getting to laser-based kilometer detection of in many different areas. There's a multitude of these new sensing technologies, and as with most disciplines, market factors of cost, volume, and profit will start to help determine those sensing technologies that advance up the TRL ladder and those that do not. So I'm going to finish with just a few references to a couple of those technologies where we might expect to see in the future the mid-IR come into play in a major way in the market. Perhaps it's just my own interest here, but I have an interest in laser additive manufacturing, which of course now is a well-established research field. There are major laboratories, particularly the Institute for Laser Technique in Aachen, where much of this technology was developed early on. But that are basically powder-based, three-dimensional metals and ceramic fabrication techniques using high-intensity laser systems, where the laser is basically a focused light source that is used for sintering of these particles into three-dimensional structures. And the potential here, of course, is that one has localized control over the composition of the materials, low oxygen content, capabilities to do repair and salvage capabilities. There is a movie here, but I'm not going to show it because of the time limit which we're running up against. But I think if you go on to the ILT website, Fraunhofer ILT website, you probably see this several examples of movies of three-dimensional structures that have been manufactured by not just this particular approach, laser materials deposition, but there are several approaches to 3D fabrication. I emphasize with near IR laser light sources in the kilowatt sort of region. The question I pose is, as we develop mid-IR, high-power mid-IR laser light sources, can these possibly have a play in advanced manufacturing? And it's my view that they do. And perhaps an importance, not in the sense of replicating three-dimensional manufacturing with 1 micron sources, but 2 micron sources, for instance, and sources at other wavelengths have the capability of being transmitted through many semiconductor materials like silicon and gallium arsenide, germanium. So this opens up the potential to be able to use high-power laser-based either 3D modification or surface modification techniques through these materials. And obviously, these materials have a great are the center of the microelectronics industry. And so, for the first time, potentially, we could be, for instance, using high-powered 2-micron light, for instance, to do processing on the backside of silicon, or three-dimensional 3D additive manufacturing on the backside of a semiconductor material, perhaps in some photonic structure that's already been created. What's shown in the next slide here is an early example of that idea, demonstrated by the Ilya Mingareev group at UCF, now at FIT. And here one shows the use of 2-micron focused pulse light to actually do welding on the backside of silicon wafers. So I'll close by just mentioning the imaging application areas in the defense and security applications area, which, as I mentioned earlier, still dominate the mid-IR imaging industry. Not all the colors have come out in these figures here, at least from what I'm seeing here, but they really are these imaging techniques are really in the domains of countering lethality, survivability, and mobility. In this photograph here, supplied by my colleague Rodriguez, you can illustrate the great differences in imaging in these different wavelength regions between the long wavelength between the visible region and the long wavelength IR regions. You see the difference in resolutions that we are able to obtain in these wavelength ranges. They're used in target acquisition, the Lantern system by the Air Force, for instance, the Sniper system by the Marines, and it's also, of course, being incorporated into the Joint Strike Fighter. In intelligence and surveillance, of course, these systems are now vital. He's shown some examples of the imaging capabilities. These are from satellites, but in countermeasures, the distributed aperture system from the Joint Strike Fighter, in large aircraft ICOM, for instance, IRCM systems. A number of industries are, of course, involved in these developments, including BAE. So, applications, in summary, applications in the mid-IR optical and laser technologies are surfacing at multiple levels across nearly all industries. Manufacturing environment, I say food, medical, domestic appliances, defense and security. I apologize, but there's no attempt here to provide a comprehensive review. I hope I've managed to interest and maybe entertain you in at least reviewing this revolution that's occurring. There are so many diverse sensing technologies. They will ultimately have to rely on more solid technological progress in more mainstream industries, in a way that's not too dissimilar from at least my experience in the last century, where the laser fusion and military applications field really drove the development of industrial solid-state lasers in the early days after the development of after the demonstration of the laser itself. The challenges near term in the mid-IR are going to be in cross-disciplinarity of developments in optics, lasers, and photonics, and new materials. And being able to correlate this with the detailed understanding of core physical sciences in chemistry, biology, material science, and equivalent, perhaps to a greater extent than the laser and optics field has been used to. There are other fields, for instance, are more used to correlating and integrating this cross-disciplinary interest. The space technology is perhaps one of them. And these sciences will not just be the hard sciences, but the social sciences as well. So human factor engineering, we all know, is playing an increasing role in industrial engineering development, and it will too with the incorporation of mid-IR materials. Many materials involve toxic materials. Many sensing systems involve toxic materials, for instance. Human factor issues will start to enter into those. Industry, of course, will be driving most of this development, so SWaP-C will be the important factor in determining not only future products, but also the R&D development paths, as I've indicated. Over here in the US, this will be largely determined by the market, by industry. But in Europe and in Asia, government programs also play an important role. So it's going to be this mixture of industrial investment and major government programs that will drive all these technologies. So let me summarize by saying that maybe mid-IR science and technology is at the hockey stick phase of development, sort of akin to where lasers were at the turn of the century. It'll be constrained amongst other factors, or the development will be constrained amongst other factors by the development and testing of new materials. If there's anything I've learned as as a laser scientist, it's been how strongly we need to understand materials in order to really make progress in designing new optical laser systems. And this applies to photonic systems too. We're going to see, I think, just putting my philosophy hat on for a moment, we're going to see that the demands of the clean world, clean energy, the higher quality of life in our environment, our sustenance, like in terms of quality of food, medical support and attention, immediacy, including defense and security, of course, that will help create new markets for optical and photonic devices. And as I mentioned before, in most of these areas now, it will be the market decides the progress of development in these technologies. I leave by just acknowledging at least my support in putting this together, my colleagues here at UCF and at FIT, and also my colleagues and collaborators at Nanyang Technical University at Singapore, my funding support from various U.S. agencies and the state of Florida, the large collaboration I have with many different companies in the photonics field, and of course I should make a point here of acknowledging the two companies that are helping support this webinar. And lastly, I'll apologize to those of you whose work I should have quoted, whose work I have misquoted, and to those who feel I have not presented a balanced view of this. And I thank you for your attention.
Okay, thank you very much, Martin. Due to time limitations, we're going to skip the Q&A session. As I mentioned, for those in the audience who want a copy of today's slides, a PDF of today's presentation is available in the Event Resources section below the Q&A box. I do want to say that this presentation is an exceptionally thorough source of information, so I do recommend downloading the PDF. On behalf of Laser Focus World and Penroll Corporation, I'd like to thank today's speaker, Martin Richardson, Professor of Optics and Photonics at Creole, for today's presentation, Infrared Sensors and Systems, an Overview and Tutorial. I'd also like to thank today's sponsors, Teledyne DALSA and Sierra Olympic Technologies. This presentation will be archived within 24 hours and can be reached from our homepage at www.laserfocusworld.com. A reminder email message will be sent to all registrants, complete with a direct link to the archive. We thank you for joining us today and look forward to serving you with future webcasts.